Okay, so let's start this afternoon's lectures. Okay, so when we consider steady state, two-dimensional, implicit, Boussinesq, and non-rotating, okay, and fluid flow, then the also small perturbation, that means linear. Then these set of equations, okay, the original set of equations can be reduced to 5.1.1 to 5.1.4, okay. And these four equations, okay, as you know, the first one is the momentum equation in x direction, and then momentum equation in z direction, height direction, vertical direction, and then incompressible continuity equation. And then also we assume adiabatic, okay. And then so we have the thermodynamic energy equation. So those four equations can be combined together in terms of W prime. Then that equation will become like this, okay, like this. And this is also called Scholar's equation. And Scholar's probably was the first one reduced to this form. And that we can write in this way, okay, same thing, like 5.5, 5.1.5, except the Laplacians, okay, we kind of write out Laplacians. And L square is equals to n square over u square. This bar is called over, okay, UGG over u, okay, times W prime equals 0, okay. Okay, so in L square defined as n square over u square minus UGG over u is the scalar parameter square. Okay, so L is called scalar parameter. Okay, so equation 5.5.5, that's this equation, is that a central tool for many theoretical studies based on that equation. Okay, and this equation also can be interpreted as a vorticity equation. Okay, a vorticity equation. Okay, and how do you interpret this as a vorticity equation? What we can do is multiply by u. So we multiply u. That gives us the following. Will be, okay. Okay, this will become W prime xx plus W prime gg, right? So you multiply it, then we got u times wxx prime plus wgg prime. Just different way to write it, except, okay, in this way we multiply u on all the terms, and then this becomes okay, becomes n square divided by u times W prime and minus u gg times W prime equals to 0. Okay. And this term is the rate of change of vorticity following a fluid particle. Okay. Understand? Anybody have problem? with this term. Okay, the physical meaning of this term is the rate of change of vorticity following the Fourier particle. Of vorticity. Okay. Anybody knows why? No? Okay. Let me give you a hint. Okay. So, del prime of x, wx prime plus wg prime, what's this? What's that? I probably write it in a kind of unfamiliar way. If I write it in a way like continuity question, very good, okay. Okay, so this means dw prime dg be equals to negative dw prime dx. Okay, so now this term is u d squared w prime dx squared plus u dw prime dg squared. Okay, and we substitute dw prime dg into here. Okay, then this becomes u, okay, d squared w prime dx squared plus u dg of dw prime dx negative. Agree? And we swap this, bring negative out. Or maybe I keep it here and then have negative dw prime dg here. Okay, and I bring one partial x out. Then that gives us, maybe I write down. You got this, I believe. Okay, this, okay.
I don't know why this equation is a continuity equation.
This is continuity question.
Continuity equation should be partial u prime partial x.
Oh, yeah, that's right. Right, that's right. Yeah, okay. So you're supposed to partial u, partial x. Right. Okay, that's very good. Okay. So I did it on purpose. Okay. Right. Yeah. So looks like some people is not okay, kind of sleeping. Okay. So this u prime dx. Okay. So then this become minus negative du dx. Agree? Right. Double check. Maybe it's not. You sure?
Yes.
You sure? Okay. You sure? Okay. I trust you. Okay. So now this become u. U prime and u prime. Now we are okay, right? Agree? Okay, good. So now you got this. Okay, so it's correct now. We can erase it. Okay, so this becomes, we bring one partial x out. We have u, right? We have u. Okay, so now we have u partial x. And then the then I write this first, negative the u dg. Maybe it's okay. Yeah, it's okay. So I have partial w prime, partial x minus partial u prime, partial g. So getting clearer now, right? Okay, so if we have partial w partial x, so right, this is w prime. So if we have partial w prime, partial x, then we have vorticity, right? Right, we have vorticity. Right, go this way, this way. So this is which kind of vorticity? It's y vorticity in y direction. Okay, but this is negative y. Okay, negative y. Okay, so this is give us y vorticity equation. So let's probably say, okay, so this is negative, the partial w partial x will be equals to y vorticity equation. So this is y vorticity. Okay, and if we have u, if we have u and partial g, so u prime, so say you have u prime, then we have this into it, right? Vorticity, and this is y vorticity. So the y vorticity is equals to the u prime the g. This is have the perturbation wind shear, okay, in g direction, right? So we can bring these two together. So our eta, the y vorticity, is equals to these both terms can contribute to it. So it'll be partial u prime, partial g, minus partial w, partial x. Okay. So basically this is this term. So this term actually equals to negative u ddx of partial u prime, partial g, minus partial w prime, partial x. But this is eta, y vorticity equation, y vorticity. So this is negative u partial x eta. Okay. And also keep in mind ddt of eta is equals to what? Partial eta, partial t, right? Plus u, partial eta, partial x. That's it, because we don't have basic vertical motion. Okay, we don't have w, the eta, dx. We don't have this because no basic, okay, W. Okay, because W is equals to W prime. Remember that? U is equals to capital U plus U prime. Okay, so we don't have this term. And then this term is gone. Why? Why? We don't have this term. Hey, come on. Steady state, not stationary. Steady state. Because steady state. Okay. So this means U partial eta x is equals to d eta dt. Okay. That's the total rate of change, okay, following the motion. So this is equals to negative d eta dt. Okay, because d dt is equals to u ddx. Okay, for steady state, two-dimensional flow. Okay, so that's why we say it's rate of change of vorticity following the fluid. Following the fluid is total derivative. Okay, so don't overlook this simple equation that has lot of meaning in it. Okay, so when you look at equation, don't be scared by it. Try to make friends with equations. Okay, if you're a girl, try to make boyfriends. Okay, you can have one more boyfriend. Okay, if it is equation. Okay, yeah, you don't want to have two boyfriends, but additional one is a equation. That's okay. Okay, it's allowed. And okay, for boys, you can have you can make girlfriends. Okay, with equations. Okay, of course you don't want to have two girlfriends, right? Yeah, just you have two girlfriends or you have two boyfriends, just like when you are eating. Okay, you有两对碗 Okay, 一个就是一个就是Okay, okay, 想不过无用啊 Okay, too busy. Okay, so but okay, make friends. Okay, with equations are good. Okay, you are encouraged to do that. Okay, so now that's total rate of change following the motion of vorticity. And this vorticity is Y vorticity. Okay, Y vorticity. Okay, now we have second term here. We have second term here. Second term is split into two. Okay, so now we are done with this one, right? We're done with this one. I'm making the blackboard, okay, very busy. So we are done with this one. We are done with this one. Okay, and now what's the meaning here? Why I say this is vorticity equation? If I say this equation is vorticity equation, that means every term has something to do with vorticity. Okay, so now why we say this? Okay, can somebody tell me what's the physical meaning? Just nothing to do. Don't talk about vorticity because I'm going to explain it. Okay, just look at this. What kind of force make this? Buoyancy force. Buoyancy force. Because okay, because n squared, and then what do we have? Divided by u, right? Divided by u, and then 30 prime. This is equals to, but n squared is equals to what? Buoyancy, frequency over theta, d theta, d g, right? Okay, so this equals to 1 over u g theta d theta dg del prime. Okay, and this is called buoyancy term because because the theta dg, okay, is oh, maybe let me do this, because theta divided by the theta dg is the ddg is proportional to negative d rho dg. Agree? Okay. Agree. Okay. So when you have density varying, that means theta varying. That means density varying. Okay. Density varying. That means you have buoyancy force because density changes. Okay. When you lift up, okay, it changes density, and then that gives you expansion, and then create denser fluid, right? Because expansion and become colder, okay? And colder, oh, where are my friends? Okay, everybody's, okay, staying so far away, and then become colder, whoo, and then shrink, okay, kind of sink down, and then passing the original level, and then at low level, because it's stratified fluid, so okay, pressure is larger, so squeeze it, okay, so become, okay, very uneasy because it bump into each other very often, so become, okay, hot, okay, and become warmer and become lighter, and then shooting up, and this is called buoyancy oscillation, and the force is buoyancy force, okay, that's, so this term is buoyancy force, okay, we explained that before, this is buoyancy force. Buoyancy, probably I would say effect. Okay, the force is buoyancy force. Okay, effect. Okay, and that's because we have gravity. Okay, bring up and down because of change of the vorticity, density. Okay, so now why? Okay, so why this is related to why this effect related to because of that affect the vertical motion. So that is so why it's related to vorticity. Why? I'll give you 2 points if you can answer that. Why? That's related to motion, right? Vertical motion. When you have vertical motion, you create, okay, it's due to buoyancy force. You have vertical oscillation. We call, okay, buoyancy oscillation. And that can create vorticity. So say if I have air parcel here, okay, I have fluid, right? And then here, I have upward motion. That creates what? Okay. Y vorticity. Okay, so this creates a pair of Y vorticity. One is positive vorticity in Y. This is negative vorticity in Y. Okay, so this is, okay, so here is positive Y vorticity. Okay, this is negative Y vorticity. Okay, so this is probably positive eta, this is negative eta. Okay, when you downward motion, and then you create a pair of vorticity, but just opposite to this. Okay, so that buoyancy force, okay, produce vorticity. Okay, so So it's a rate of vorticity production. You produce it. Okay. When you have upward motion, you create. Okay. Remember I draw this figure. When you have a thunderstorm, we have upward motion here. Okay. And then here we'll create vorticity, and that gives us secondary circulation. Okay, so this is the rate of vorticity production by buoyancy force. And then negative UGG W prime. Yeah, try to, actually required, use English to do the homework, okay? Because in Taiwan, okay, every day people talking about we wanted to internationalize, okay? We wanted to 国际化, okay? But some simple thing you really have to 国际化, okay? Very simple thing, very easy. For example, when you talk about the NBA, okay, games, okay, why don't you put English there? Okay, you can have translation of Chinese, the name, but why don't you put English there? And you translate a team into Chinese, that's fine. But why don't you put a parenthesis in the original English name? Sometimes I read the Chinese news online. I don't know what they're talking about because there's no English. Okay, and you want to 国际化, you have to use that. Okay, it's fine. Okay, we translate into Chinese. Okay, and then put it that way, but put a parenthesis there. Okay. Okay, so negative UGG W prime. So how do you interpret this? Okay, now it's your turn. Okay. Okay, yeah, do it. Okay, yeah. And tell me what you find. Can you find why I say that? Okay, and oh, disappear. Okay, yeah. So what's a physical meaning there? Try to play around with that term. Okay, play a little bit. Okay. Well, I give you a hint. Okay, I give you a hint. Okay, bring back, but try to write in a way. Try to interpret what I said is. So when you look at equation, okay, you have to kind of try to make friends with the equation and try to interpret it. And later, once you understand it, you have a very deep understanding of the equations. And then that gives you a lot of physical meaning and help you to understand the equations and, okay, then understand the mechanism. So how do you interpret that?
I think it's kind of observation.
Observation. By W prime. Okay. So you just have to rewrite it, right? You just have to rewrite. That's very good. Okay, very good. So this one, you write this way: negative W prime, the square, U, the G square. Okay. And then you write W prime, the G of the U, the G. Okay, and what's the U, the G? So this is X, this is G, torsion, and this is U. Right. So this is U, capital U. Okay. So this is capital U, U of G. Okay. So what's the U dg? That's produce the vorticity, right? Yeah. Go this way. You put the leaves here, and that will turn this way, and that is into what direction? So this gives you, okay, Y vorticity, but that Y vorticity is different from that Y vorticity. Okay, this Y vorticity is associated with basic flow. Okay, Y vorticity, okay, of basic flow, associated with. I probably should say associated with basic flow. And then this is advection by perturbation wind, not advection by basic wind. Normally we talk about advection by basic wind, okay. But here is perturbation, okay, advection. So this is advection, okay, by W prime of, okay, eta vorticity associated with basic flow. Basic flow is U, okay. Okay. Or you can say advection of the basic flow shear, okay. But that shear actually is vorticity. Okay. So now if you look at this simple equation, and now you interpret this way, okay, then you have pretty good understanding of what's going on. Okay, so that's basically its vorticity equation. Okay, basically this is vorticity equation. Okay, it just write in a way you cannot see it. Okay. Okay, so everybody okay? Okay, so this equation, like before, we can, okay, look at the extreme cases. So I guess I can erase this, right? Okay. Okay, if extreme cases, okay, extreme cases. First, if n square is very small, it's very small. That means this term is very small. That means this term is much smaller than these other two terms. That means the vorticity produced, okay, by buoyancy force is minimal, very small, okay, compared to other terms. Okay, because this total rate of change. Okay, okay, or advection or the Y vorticity by U wind. This is advection of basic wind vorticity by W. Okay, prime. So if this is very small, then of course this term will become. Then the equation, this equation will reduce to the following. Reduce to u wxx prime plus w gg prime. Okay, and also we assume. Okay, we also assume. Okay, no wind shear. No wind shear. Okay, or constant wind shear. Okay, that means Ug is equal to 0 or Ug is constant. Okay, and both of them gives us Ugg. Both of them give us Ugg equals to 0. Okay, so then in this extreme case, this term is almost 0. This term is almost 0. So the equation reduced to this one. Okay, and that is that reduced to the u, and then 30 prime, 30x square plus u, 30 prime, 30 square, 30 prime, dg square equals to 0. Okay, we divide by u, and u is not 0. Okay, u is not 0. So, okay, we divide by u, then this becomes d square 30 prime, dx square plus d square 30 prime, dg square equals to 0, or we can write in this Laplacian equals to 0. And this is called what? We discussed this before. Okay, so now you bring back what you learned earlier. Okay, when we talk about pure gravity waves, we say this is what? This is representing the potential flow, okay, or irrotational flow. Okay, so this is extreme case. Okay, so that means the stratification is not very, it's almost 0, very small. Okay, so if stratification is very small, that means the fluid is like water. Like water. Okay, so with like water, that means, okay, your pressure is not, okay, like stratified fluid. Your stratified fluid, okay, then then when you bring the air parcel or fluid go up, then the environmental density is same, right? Because it's same density. Density is not changing. So you bring this air parcel or fluid, maybe fluid, okay, go up, it's same density. So you don't change, okay. You don't change density, right? Because it's same. You don't change density. So then you don't have the distorting force.
It's the same thing like
More or less like that, yeah, okay. Close to it, okay. Probably even stronger than that, okay. So you don't have buoyancy force. You don't have any force to bring it back. That's called distorting force. Okay, so then you don't have wave generated. And then in that case, we become this irrotational flow, okay, and or potential flow. Just like our friends in engineering school, they study, okay. They don't care about these gravity waves, and then you don't have gravity waves generated. Okay, that's called potential flow or irrotational flow. Okay, so we studied that in chapter 3, okay, the 3.5.22. See, chapter 3 of Dean 2007 book, okay. In our lecture note, that is probably chapter 4, okay, chapter 4. That pure great web chapter. The buoyancy force is negligible in this extreme case. Okay, so now second part of this chapter we are going to do is to recognize the regimes of stratified flow over I probably should say the sinusoidal mountains. So you probably want to change your note if you print out these sinusoidal mountains. Okay, so now we are start to work on the mountain waves. Okay, so the forcing will be mountain. So now we have low boundary condition is no longer flat surface. We have mountain. But mountain, when we have a kind of like a pear-shaped mountain, it's too complicated. Okay, so before we do the complicated form, let's just work on kind of sinusoidal mountain. Okay, just like a sine curve. Okay, very simple, right? Okay, so you study that kind of simple case that give you very simple problem, like simple solution, and you can look into the details of what's going on, in-depth dynamics. And then later we study the isolated mountain, which is what the mountains in the real world, we are looking at. And then, but since we studied this already, we have some basic knowledge. So then when you study more complicated problems, you just have to worry about the additional complication part. But some basic part is, you can easily, translate into here from your study. Okay, so we are going to look at this sinusoidal mountain first. Okay, yeah. Of course, you cannot find that kind of mountain, in the world. Okay, sometimes you do. Okay, in some area which you have Piedmont. Okay, Piedmont, like in North Carolina, like the place I live, like a place Chia Hong lives. We live in different cities. Okay, I kind of take trains every day. Okay, and one way is 75 minutes to school. Okay, so but we all in the same area. Okay, which is called Piedmont. Okay, anybody knows the meaning of Piedmont? Piedmont. Anybody? Okay. Turin D. Okay. Piedmont. Okay. Piedmont. Okay. So here's small hills. Okay. So here's small hills. Sometimes, sometimes in one of the trees on the street, it's like this, like sinusoidal mountain. Okay. Every time I kind of drive through that, this is the mountain I've studied. Okay, like that. Okay. And do you know the difference of here and the mountain? Higher is mountain. Okay. Small one is here. Okay. Here is normally is under 1 kilometer. Okay. It's here, like in England. Okay. They don't have mountains. Okay. They just have hills. Okay. They don't have high mountains. Okay. And here we have high mountains. Okay. So. Yeah. Okay. I guess I probably let me see. So we are going to study this. So probably I kind of take a break now, and then for 10 minutes, and then we start this. Okay. Okay. Rather than kind of start here and just a few minutes, and then we stop. Okay. So we'll start from here for the next lecture. Okay. So I just make sure everybody got Chia Hong's email, right? Okay. So now you're supposed to be able to do the problem. You got everything. Okay. You got name list. You got ACL, protein, right?
They still use they need to still use the grades.
Grades is fine. You can use either grades or NCL, right? But you did a pass to them, right? Yeah, okay. Yeah. Okay, so let's take a break or 10 minutes and then come back. Okay. Yeah. Okay, there's a question. There's a question about how much percentage of the final exam. Okay, and so here, in one of the syllabus, I have homework contribute to 30% of the total grade, and the final exam 35%, and project 35%. We probably have to change this, because this was when I taught at North Carolina, and we have the whole semester. So that means I can give more, okay, projects and homework. Okay, and here we squeeze in, so we cannot have so many homework and project, because you cannot digest. Okay, that's the reality. Okay, if I were you, I couldn't do it too, because then you are going to have almost every day you have okay, homework. Okay. Or every other day you have homework. Okay, that's impossible to do. Okay, so I think to be reasonable, to be fair, to be reasonable, I think we have to reduce. I have to reduce the percentage of the homework and project contribution to the okay. And final exam will be probably more. Oh, I saw that you're like, oh, yeah, okay, yeah. This is democratic society, right? This is not like China. This is Taiwan, right? This Taiwan is democratic process. Okay, so we can vote. We can vote. Yeah, we can vote. Yeah, we can vote. Okay, but one thing you have to be careful is, okay, open book. Normally, CC open book, right? So normally the problems will be okay. Not only tougher, much tougher. Okay. So but we can vote. Okay. Everybody prefers. Okay. Everybody prefers to have the open book. We can open book. Okay. Yeah. But I tell you, course book. Okay. My final exam. Okay. It's not that difficult. Yeah. Yeah. It's not difficult. Okay. Okay. I have a pretty high percentage. Kind of very short questions. Okay. Yeah, very short question, very short. I just ask questions. Okay. And just probably just maybe 2 or 3 problems. Okay. Which involve probably derivation equation or okay, dealing with equations. But okay. And if you're dealing with equations in those short term, the short questions will be kind of very short, very simple. Okay. So you never know. You probably will eventually you will say, oh, Dr. Lin, can you give me 1 more final exam or 2 more, because you enjoy it, okay? Right? He's a witness, okay? So yeah, right? You enjoy it, right? Okay. Okay, so and probably I will give maybe probably I'll give about maybe 15-20 minutes. Okay, so they can start. They can work on the project. Okay, and we probably can design. Okay, maybe second project. Okay, actually I try to design 4 projects. Okay, but then I think maybe too much for you. So I reduced to 1, but then now I think it's 2 days. Okay, we need more. Okay, and because I found amazing. Okay, I found okay, there are some okay details. Okay, are pretty good. Okay, so you okay without much information you can work something not quite, but it is close enough. Okay, so probably we can have. Definitely we have to have 1 or 2 more projects. Okay. Other way we can do is we have more projects. Okay. And then we have this contribution from the final.
Yeah.
That's fair. That's fair, right? Right. That's fair, right? We have more projects. We do more projects.
Okay.
Okay. And then we still need to have final, but okay, we reduce it, the contribution. How about that?
Okay.
Yeah.
Good.
Right. Yeah, because practice also you have some feeling about the gravity waves, and okay, and maybe we can have two, okay, two more projects. Yeah, okay, and then you have some feelings about it. Okay, yeah, that's other way we can do. Okay, but think about it. Any suggestions? I'm open. Okay, this okay, democratic society. So just vote. Okay, yeah, yeah. Except don't occupy. Okay, okay. Don't occupy this place. Okay, okay. Yeah. Don't bring your sleeping bag and occupy okay the whole area here. Okay, so I can still give lectures. Yeah. But we can discuss about it. Okay, yeah. Once we get more into the lectures, you have more feeling about what you want. Okay, and once we do more project, you okay. Maybe we can still do more. Then okay, two more. Maybe you can three more. Okay, yeah. Okay, yeah. So we'll see. Yeah. Okay, now first thing is trying to use very simple problem to help us to get more deep, in-depth understanding of the problem, okay, or the fundamental dynamics. So that's why, okay, to avoid some complications of mathematics, we just use sinusoidal wave, okay, and not wave, the mountain sinusoidal. So we assume mountain is sinusoidal. It could be cosine function. It could be sine function. So we just simply use sine function. Okay, so we assume we have a sinusoidal terrain that h of x equals to hm, and then sine kx. So that means we only have one k. So then our mountain is like this. Okay, and so from the mountain peak to mountain peak, that is the wavelength, and this wavelength is terrain wavelength. Okay, terrain wavelength like that. Okay, so k, okay, will be 2 pi divided by L. Okay, again we are talking about angular, okay, frequency, angular wavelength. Okay, wave number. Okay, so we have like this. Okay, so now first thing is what's the difference from what we studied before? Okay, the equation is same. Okay, only thing is now we have forcing, and this forcing is the terrain like this. Okay, so only thing very important is different from before is we have very clear low boundary, and this boundary is different before. Okay, before was flat. Okay, terrain. You coming in, okay, and then you can have disturbance, but at surface, the low boundary condition is what? What's the low boundary condition here? We used before. It's W prime equals to 0 at G equals to 0. Okay, so now we no longer have that case. Okay, and basically, no matter what kind of rigid boundary, basically, if we have rigid boundary here, we have rigid boundary here, right? The OR. Okay, basically, your boundary condition is this: your flow comes into here. Okay, you cannot penetrate into it. So the vertical component, perpendicular component of the wind at the rigid boundary will be 0. Okay, so here, if this is vertical plane, right? Vertical plane. So you can have W near the boundary here, but you cannot have U wind into it. U will be equal to 0 here. Okay, U will equal 0 here. And you can have V here. Okay, so flow comes in to here, will spread out, cannot penetrate. So you can have W, you can have U, but you can have V, you cannot U. Okay, so if this is if here, then also flow comes in, you cannot have V wind. V will be 0 component. Okay, so say this is X and G plane. So this is V wind come to here will become 0, but you can have U and W. Okay, and down here too. Okay, down here you can have U. Say this is low boundary. Okay, so it's no mountain. Okay, so same principle. You have flow perpendicular to it will become 0. That's W will be equal to 0. Okay, and flow will spread out. So you can have U wind, you can have V wind, doesn't matter. But you cannot have perpendicular component of the wind, okay, at the rigid boundary. Okay, so here, now we are okay here. Now, what's the boundary? So assuming there's no viscosity, so it's invisible. Okay, that means no viscosity. No viscosity. So now you have you assume since no viscosity, so you assume your flow will be forced to follow the terrain. To follow the terrain. Okay, to follow the terrain. So your flow will be like this. This will be flow. Okay, this will be flow here, and here will be parallel. Okay, here will be parallel, and here will be like this, like this. This is your flow. Okay, so this flow has two components. Here U and W. Okay, I'm talking about perturbation wind. Okay, and that has to be parallel to the mountain. So parallel to the mountain is what? This is, what's this? Mountain slope. So how do you express it mathematically for the mountain slope? Okay, so mountain slope. Okay, very good. So that is partial H, partial H. Okay, so that means what? W prime over U prime. That's the slope. The flow follows the terrain. That equals to dH, or maybe just simply say like this, dx. Right. Right. This is a slope of the flow must be equal to the slope of the terrain because it has to follow the terrain everywhere. That's the low boundary condition at G equals to mountain, right? Mountain height, H of H. This is low boundary condition. Okay. So that means W will be equal to U dH dx at G equals to H of X. That's low boundary condition. Okay, now we are working on the linear problem. Okay, so this W is equals to 30 prime. Okay, we kind of write in perturbation form. So U is equals to capital U plus U prime. Okay, and H is H. Okay, of course we are assuming, okay, kind of small amplitude. Okay, so now we have this become complicated now. 30 prime equals to u plus u prime dh dx. Okay. So, and then at g equals to h of x. Okay, so that's the low bound condition. So don't overlook. Anybody knows what's overlook? Don't 小看, okay? Don't overlook, okay? Don't overlook the low bound conditions. It's very complicated. Okay, it's very complicated. It's a nonlinear problem. Okay, nonlinear problem. Why? Because if u prime is large enough, then you cannot ignore it. Okay, so and then so this term become appreciable, become large, comparable to this capital U, and you cannot ignore it. Okay, so in order to simplify the problem, okay, we also we treat the governing equations. We ignore this one. So we assume, okay, so we assume, I guess I can get rid of this now. Maybe I can get rid of here. Okay, so now we have this. So we linearize the low bound condition. We have two nonlinearities. This one is one of the nonlinearity, okay, and other one is this one. Because you have to apply the low bound condition at that location. Okay. So there are two nonlinearity. So we try to simplify the linearize the low bound condition. Okay. So first one is assuming less than u. Okay. So then that gives us 30 prime equals to u partial h partial x. Okay. Like this. And second thing is we assume the mountain height is very small. It's small. Okay. So it becomes kind of linear mountain, very small mountain. Okay. So then the apply this at g equals to 0. Otherwise, don't overlook at that. Or otherwise, you cannot solve it linearly. Or you cannot solve it analytically. Okay, not that easy. Okay, you can solve it, but you have to use computer to iterate. Okay, apply it the mountain surface. You apply it. Okay, mountain surface. You cannot solve it. Okay, using your pencil or your pen. So we linearize two parts. This on the nonlinearity, other nonlinearity. Okay, so we apply it to g equals 0. So this is our linear low bound condition. Okay, and this is our terrain. Okay, this linear bound condition. So once we have that, then okay, we can try to solve it. Or other thing is when you assume there's no friction, and then the flow will be flow kind of freely around the terrain. That's called the it's called the free slip. Okay, free slip with low bound condition. And sometimes you see some wording like non okay, no free, okay, no non-slip, okay, low bound condition. Low bound condition, okay. You have non-slip, low bound condition. That means you have friction. So when you have friction, then you have friction. So mountain slope, you have friction. Okay, even in flat surface, your U always equal to 0. Okay, at the low boundary here, always equal to 0. You cannot have free slip, kind of freely going over. Okay, and then in that case, it's more complicated. You have to use the model to solve it, because when you have boundary layer, okay, and as you know, boundary layer has two effects. What are they? What are the boundary layer effects? Have two effects. One is, okay, one is friction. In boundary layer is friction. So that has frictional effects on the atmosphere. And other one is heating or cooling. Okay, so that's boundary effect. So you have a boundary layer, then here your U, V, W at the boundary is 0. Okay, and then on top, then you can have flow. And that's called no slip boundary condition. I think it's probably called no slip boundary condition. No slip boundary condition. Okay, so two types. We are going to use this one. Okay. Okay, so now, okay, we have this, we require the free particles to follow the terrain. Okay, so we have this, okay. W over U equals to W prime over U plus U prime equals to dH dx. Okay, since we assume H is only function of X direction, so we have the dH dx. If H is three-dimensional, then we use partial H partial X. Okay, so for 2D, then we can have 30 prime equals to U dH dx. Okay, at G equals to 0. For 3D, then 30 prime is equals to what? U partial H partial H plus V partial H partial Y at G equals 0. Okay. Yeah. You have three-dimensional flow. Okay. Okay, so we are done with that. Okay, so now for a small amplitude mountain, then we can apply at G equals 0, and also we can simplify, because small amplitude mountain means it's going to produce smaller perturbation in U. That's U prime, right? So U prime is much less than capital U, so we can ignore that U prime when it compares with capital U. And then that's why we can have this U here. Okay. And also that's why we can apply at G equal to 0 instead of on the mountain surface. Okay. Okay, so now once you have that, then then H is equals to HM. HM is mountain height. Okay, mountain height. Okay, it's mountain height. So when we have sinusoidal mountain, so this is HM. Okay, and this is L. Okay, and then K is equals to 2 pi divided by L. Okay, like that. Okay, so now we have H and we have this. So that gives us 30 prime equals to U partial X of this h of x, okay, that is hm times sine kx. So that gives us u times hm and then ddx of sine kx. And sine kx, the differentiation of sine kx will be equals to cosine kx multiplied by k, right? So then we have u hm times k and then cosine kx. Okay, so this is our low bound condition now. Combine the particular mountain geometry and then, okay, with this low bound condition, we got this. And this is for this sinusoidal mountain, we have this. And so this is applied at g equals to 0. Okay, so now we have low bound condition. Okay, so now we have this. And you can write this one as w prime of x and then g 0. 0 means g equals to 0. Okay, that's 5.1.11. Okay, so now we can start to solve it. Okay, and so the mountain is sinusoidal, and that disturbance will be also sinusoidal. Okay, yeah. 龙生龙，凤生凤. Okay, so you have this, right? So you assume the disturbance, okay, will be sine function or cosine function. Okay, in general, it's a combination of cosine and sine function because both of them are allowed. Okay. You don't anticipate your mountain is sine function, and then on top will be sine function. Okay, because you should allow cosine because you could have shift of the phase. Cosine and sine has different phase. Okay, so but you should allow that. Okay, because the phase could be shifted. In other words, when you have mountain height here, it's not necessarily your wave will be maximum here. Your wave, that peak could shift, and that is because of cosine. So you need to allow both cosine function and sine function. Okay, if you just allow sine function, then you can still get solution, but your solution is partial, not complete. Okay, so we need to have this. Okay. So so this is our low bound condition now. We're down here, we're down here. Okay, so now at 30 prime of xg, okay, we have two parts. One is we call W1, okay, of g, and then cosine kx plus W2 of g, that is associated with the sine part, like this. Okay. And then we can substitute this into the equation 5.1.5, that is WGG, okay, WG plus, let me see, what do we have? We have, okay, I think what we have is, we have partial x square plus partial square, partial g square, w prime, w prime. Okay, and then plus a square over u square, and then the square w prime, the g square, I think the x square. dx square. I believe that's correct. Okay, let me double check it. I believe that's correct. That's this equation, right? So here will be like this. Laplacian. Okay, that's Laplacian. Partial square, partial x square plus partial square, partial g square of w prime. And then we have L square. That's the scalar parameter. Okay, that's equals to n square over u square minus, okay, UGG divided by u. Okay, so here we assume no wind shear. The basic wind has no shear. Okay, so this is gone because we assume, okay, uniform. We call uniform flow. That means no shear. Okay, so UG is equal to 0. Okay, so it is. So then the L square of G becomes L square because constant. Then we got, we assume N and U are constant for this particular simple problem. So then we have this become N square or U square. So, okay, I'm correct. Okay, here. So then, oh, we don't have dd x square here. We don't have dd square x here. We don't have W prime. I remember we have that. Let me double check. 5.5.2. I believe we have that square root, square there. Do we? Okay, so now we let's assume that prime equals to before we use W head, right? Like this. And then e to the I kx minus omega t. Remember that? Okay, we have that. But, okay, since it's time dependent, it's steady state, so we only have ik. Okay, we only have ik. So now we only have simple problem because, okay, we only have ikx. Because we don't have omega equal to 0. Because omega is corresponding to partial t, negative I, like that. So if this is steady state, partial t equals 0. Okay, so we have this. So then we can, okay, we can kind of transform into Euler number space. And partial x will be corresponding to what? Partial x. I, k, good. Okay, so here ik, so you have ik square, and then the w head plus w head gg. Okay, we keep this. Okay, and then plus n square over u square, and then w head equal to 0. I believe we should have xx here. That's why I kind of write xx here. I believe that's what we learned earlier. Okay, that's what we learned earlier for pure graded waves. Right? Yeah, we should have, but otherwise we cannot have k squared here. Okay, so here is probably typo. It's a typo. Okay, it's kind of typo means, okay, typographic error. Okay, so your typo, we call typo. Okay, that means, okay, typographic error. That means you type, you mistyped something. We call typo. Okay, so that's why I kind of always write dx here. D square double prime dx square. Okay, and so now here we also have ik square equals to 0, like that. Okay, so then we have negative k square w hat plus w hat gg, okay, minus n square k square divided by u square. This, okay, and then that gives us the following: w square gg, okay, and then minus something wrong. Okay, and then minus, okay, minus n square over u square plus 1 k square, not correct. Okay, something wrong. Okay, equal 0. This is supposed to be plus. This is supposed to be negative. Okay, something wrong there. Let me see why. Parameter. It's a good thing of teaching is because if something wrong, once you teach it, you find it, okay, and then you can correct it. Yeah, that's a good thing of teaching. Let me double check on this.
I have a suggestion. Maybe,
Yeah.
we can start here for them to practice the project 1 and
Okay, yeah, let's do that. Yeah, let's do. Let me double check on this. Okay, I believe what I wrote, my comment is correct. Okay, but let me double check. Probably my note is not quite correct, but typo. Okay, yeah, we type too much these days. Type. So you guys. Okay, kind of do this too much. Okay, type too much. Okay, so yeah, go ahead. Let me double check it. Okay, so
we start here, right?
yeah, we stop here, and then you, yeah. Do you want to? We are almost 50.
Yeah, only 5 minutes.
5 minutes.
Or they then practice.
Yeah, probably, yeah. Okay. Yeah. So what Chiao suggested to is probably use a few more minutes to, probably still good because if you have questions, they can ask us. Okay, so try to practice that project 1. Okay, yeah, right now. And your questions you can ask. Because now you have everything now. Okay, you should be able to, okay, compile the program and
How about the format of the project?
format.
Yeah, the format.
You do it first, okay, and then let's worry about probably discuss the model, okay. Yeah. So you try to, okay, to run it, to produce results, and then we worry about how to write it, okay. Yeah. Yes.
I think this square is related to this equation, and this is equal to this equation. So they have this square term.
Right. Yeah, right. I think you're right. It's yeah, because here we have this term, right?
Yeah. But this we don't have this term. So this
So this is correct. Yeah, looks like correct. Yeah.
is all correct.
Yeah. So yeah, because the unit also doesn't check. Yeah. So should be W prime. Yeah. W prime. Right. W prime. Right. Yeah. Okay. Yeah, because otherwise the unit doesn't check. Here we get meter per second, right? And then here we have meter square. So that gives us per meter per second. Yeah, you're right. It's because of that the partial U, partial X term. So I think this is correct. This is correct. Okay. Yeah. This is correct. Okay, yeah, can work on the problem, project, work on the project. So your questions you can ask me or Qiahong.